My dearest friends, hello to you all. We have now completed 3 lessons on integral calculus together. I truly hope that through extensive practice, you have gained sufficient skill and mastery in this topic. Let me quickly summarize what we have covered in our previous 3 episodes and what our plan is for this particular part. In those 3 previous parts, we first discussed the very fundamentals of integration. Specifically, we focused on problems where integration could be carried out by converting multiplication into addition and subtraction. In the second part, we realized that some multiplications and divisions cannot be converted into additions and subtractions. So what do? We use the method of variable substitution. And in the third part, we explained that some variable substitutions necessitate trigonometric substitutions, and in that section, we thoroughly discussed trigonometric substitutions. Now, today we want to step a little bit away from trigonometry. We have grown quite tired of seeing so much trigonometry. We really want to move on from trigonometry. Let us talk in detail about fractions. Is everyone ready? Let us get started with fractions. So, let us move on to the partial fraction method. Its very name already makes it clear what it is used for, does it not? In fractions, naturally. Now, before I even begin to teach you about integration, we will first discuss in great detail, with the help of partial fraction decomposition, the entire process of breaking down fractions. Let's go see what we're going to do. It says that in order for us to properly decompose an algebraic fraction, we first factor both the numerator and the denominator of the given fraction. Subsequently, we express this single fraction as a sum of multiple simpler fractions. So when we are presented with a fraction, our initial step is to factor its numerator and its denominator. After that, we convert this complex fraction into a sum or difference of several other simpler fractions. But how exactly, what particular properties should these other fractions have? We will discover that together. It states that the denominator of each fraction is one of the factors of the original denominator. That means the denominator of each of these fractions is a factor, and I will explain them to you now. Then you can keep these notes for yourselves. You will look at the solutions to my examples and check whether these characteristics I am describing are present in them or not. So, 1. The denominator of each of these fractions must be one of the factors of the original denominator. 2. If a factor in the denominator of the main fraction has a power of n, it will be converted into n separate fractions. This means, for example, if in the denominator of your initial fraction after performing factorization you have a term, a parenthesis, raised to the power of 3, then this power of 3 itself will transform into 3 distinct fractions, and you will soon understand how this works. The next set of properties or characteristics states that the numerator of each fraction is written in a parametric form, and its degree is always 1 less than the degree of the corresponding denominator factor. What exactly does it mean for the numerator to be written parametrically? So we have a polynomial in x whose coefficients are unknown, represented parametrically. As I said, you will see this easily when solving problems. You will set the rules aside, and then you will see how I solve these problems. Alright, once we have completed this, we have 2 distinct paths. One approach is to find a common denominator and then set the numerators equal. The other method involves simply plugging in numerical values. In certain situations, this one is easier. In others, that one. I will solve a few examples for you using both methods so you can see. Let us solve examples together. Alright, we are going to decompose x plus 2 over x squared plus x. Now pay close attention because we are not going to integrate it yet. For now, we will just practice decomposition together. After we learn decomposition, we will also take integrals of these. Okay, in the first fraction, x squared plus x is in the denominator. The numerator cannot be factored further. It is clear that x squared plus x can be factored by taking out an x. So I factor the denominator into x times x plus 1. How many factors do you see in the denominator? Ignore the numerator. You will only see 2, no more, no less, if there is no problem. The denominator is x times x plus 1. See the factors, so I will convert the fraction into 2 partial fractions. Both factors are first degree, so each one becomes a single fraction. The first fraction, I wrote x as the denominator. For the second, I wrote x plus 1. I broke it down into 2. Now, what about the numerator? The numerator was supposed to be 1 degree less than the denominator. What does that mean? The denominator, the first fraction, is x. Its degree is 1. I want the degree of the numerator to be lower. So what should I write? We need a constant term, which is x to the power of 0. That is just a constant. So I simply put a in the numerator. The denominator of the second fraction is also of degree 1. Do you see what I'm pointing out? X plus 1 has degree 1. I mentioned that the degree of the numerator must always be less than the degree of the denominator. This is because, since the denominator is first degree, we write a single constant b in its numerator. You see, when I mentioned parametrically, I meant that I did not assign any specific numerical values to a or b. I have converted this into two fractions. Well, I want these two fractions to be the same as the original fraction. What do? For now, I will use the common denominator method. On the right side, I will find a common denominator for the two factors I have written. Hopefully, everyone knows how to find a common denominator. I do not know in which grade you learned this. You learned it when you were very young, but you probably remember. I will find a common denominator. The common denominator will be x times x plus 1. The first fraction's denominator was x. Now it is x times x plus 1. I multiply an x plus 1 in the numerator of that one. I multiply an x in the numerator of this one. It becomes ax plus a plus bx all over x times x plus 1. Now, the denominator of the expression I wrote is x times x plus 1, which matches the denominator of the original fraction. So what I wrote is consistent with your problem. Now, the denominators in our problem are the same. The denominator of the original fraction is x times x plus 1. The denominator I wrote is also x times x plus 1. What is the numerator of the original fraction? What is the numerator of the fraction in our problem? X plus 2. The numerator I found was 8x plus a plus bx, and I factored out an x from the x terms. You see, it became a plus b times x plus a. The denominators are the same, so this fraction must be equal to that other fraction. When the denominators are the same, there is no other way but for the numerators to also be equal. The numerator of the original fraction is x plus 2, and the numerator of my fraction is a plus b times x plus a. These two must be equal to one another. How? What is the coefficient of x on the left side? What is the coefficient of x on the right-hand side? It is a plus b, so a plus b must be equal to 1. We call this the method of equating coefficients. It is a mathematical approach. All right, let us look at the right-hand side. On the right-hand side, the constant term is a. Now, what is the constant term on the left-hand side? It is 2. These two values are supposed to be equal to each other. Therefore, a must be equal to 2. I found the value of a2. What was the sum of a and b? It was 1. What does b become? Negative 1. I have found a and I have found b. So, what does my fraction actually become? It becomes 2 over x minus 1 over x plus 1. See, I have converted a fraction whose denominator was a product into two fractions. Let us look at another type. Okay, x plus 1, the numerator does not factor further. The denominator is x times x squared plus 3. It does not factor further. So how many factors do you see in the denominator? Excellent. 2. One is x and the other is x squared plus 3 to the power of 1. This counts as one factor, x squared plus 3 to the power of 1. How many of them did you see? 2. So how many will be converted into? 2. I am going to convert it into two separate fractions. One has a denominator of x, the other has a denominator of x squared plus 3. Okay, it was decided that the numerators of the fractions should be 1 degree less. So for the first fraction, since its denominator is x, its numerator becomes a. The denominator of the second fraction is x squared plus 3. Oh, right, yes. Did you not say that if the denominator had a power, we should write as many fractions as that power? Yes, I did say that. However, that is only if the entire factor had a power, meaning if it was x plus 3 squared, then I would write 2 of them. This x squared plus 3 is to the power of 1, so one fraction is enough for us. So I wrote one fraction with x squared plus 3 in the denominator. What do I write in the numerator? What is the degree of the denominator? 2. The numerator's degree was supposed to be 1 less than the denominator's. Now, since the denominator is of degree 2, the numerator must be of degree 1. Therefore, we write the numerator as bx plus c. Why is that? Because I already used a in the first fraction. We cannot write ax plus b here anymore. This is another constant. It is bx plus c. Okay, I have prepared two fractions. One is a over x, and one is bx plus c over x squared plus 3. Now, what do? Common denominator. We find a common denominator. We multiply these together. The x squared plus 3 term is multiplied by a. Now, on the right side of the expression, I have an ax squared term. I also have a bx squared term, so I will combine them. If I factor out x squared, it becomes a plus b times x squared. What else do we have here? We have the cx term. And what else is there? We have the 3a. I have everything all sorted out. Look, the denominator on this right side is the same as the other ones. It definitely is. So the numerators must also be equal. Now, what do you see in the numerator on the left side? X, that term is on the left side. What do you see in the numerator on the left side? X plus 1. What do we see on the right side? A plus b, x squared plus cx plus 3a. On the left side, since there is no x squared term, its coefficient is 0. Therefore, on the right side, we also should not have an x squared term. If we do, its coefficient must be 0. So, a plus b equals 0. On the left, the coefficient of x is 1. On the right, the coefficient of x is c. So c is equal to 1. Well done. On the left, the constant term is 1. On the right, the constant term is 3a. Excellent. So 3a is equal to 1. Therefore, a is 1/3. Okay? Our A result has come out. C has also come out as 1/3. We are pleased. A plus B was supposed to be 0, so B must be negative A. So B is equal to negative 1/3, okay? Now I'm going to substitute the values. If we substitute 1/3 for A, that term becomes 1/3x. We will substitute B, and we will substitute C. What exactly are we doing at the moment? We are currently decomposing this fraction. So how do we integrate this, you might ask? Many of these concepts you are already familiar with. I covered them in the previous segment. But at the moment, we are separating them. Why are we separating them? Because as we stated, we cannot directly integrate products or quotients. All right, let us move to the next example, 1/x² times x² plus 2x plus 3. You see, this one cannot be factored any further. I see two factors. One is x² and the other is x² plus 2x plus 3. Or my first factor is squared. I told you that when the exponent is 2, 3, or 4, we must write it that many times. What do I mean? I am writing x² as a over x to the first power plus b over x². Oh, did you not say that the numerator should be 1 degree less than the denominator? Why are we considering the main factor? What exactly does that mean? It means the factor underneath the exponent, specifically the x itself, which is considered first degree. Therefore, in the numerators, we will write constants a and b. So my friends, since this factor has power 2, we will have two separate fractions, one with x as its denominator and the other with x². In the numerators of both, we have 1a and 1b. What is the next factor? It is x² plus 2x plus 3, all squared. So the degree of the denominator's factor is 2, and therefore the degree of the numerator, excellent, is 1. The numerator must always be 1 degree less than the denominator factor. Okay, so we write the numerator as cx plus d, and the denominator remains the same. Find a common denominator. Do not worry about it. The common denominator is not difficult. But I will tell you about the other method after this question. There is a slight distinction between them overall. It is a very mechanical process. To be honest, it does not really require much creativity. Unlike the variable substitution method, where we had to very cleverly decide what to substitute, in this method, the work is mostly mechanical, meaning it is quite clear what we are going to do. There are a series of fractions. Step by step, we will separate them using the methods I will explain. All right, let us continue with these. Then we take a common denominator. The denominator of the first fraction is just x, so its numerator must be multiplied by x times the quantity x² plus 2x plus 3. The denominator of the second fraction is x². What is it missing? x² plus 2x plus 3. So we multiply the numerator b by x² plus 2x plus 3. Now, what is the third numerator? It is cx plus d. What is it currently lacking? It is missing an x². So we will multiply this numerator by x² as well. We are going to start categorizing now. All right, what do we see on the left side? Just a single humble number 1. So we will go ahead and place that one. Now, on the right side, we have just a single one. So everything on the left side that contains an x term must be eliminated. The coefficient of x³ must be 0. The coefficient of x² must be 0. The coefficient of x must be 0, or only the constant value will remain. B will then be determined as 1/3. If b comes out as 1/3, it helps us solve the rest of the equation system. In the third equation, we had 3a plus 2b equals 0. When we substitute b equals 1/3 into that equation, we obtain a equals negative 2/9. All right, a is found. Now we substitute this value of a into the first equation, and c will be found. Excellent. C is found, a is found, b is also found. We place it into the second parenthesis, d is also determined, and the fraction has been fully decomposed. Now that it has been decomposed, we are going to integrate it later. But for the moment, we are only separating the fraction. I'm going to leave this particular question entirely up to you. How many distinct factors does the denominator have? What exactly is its exponent or power? Based on that power, write down the correct number of fractions and then write down all of the numerators. Find the common denominator. Although I will solve this problem using a different method, one that doesn't involve a common denominator, I encourage you to use the common denominator approach and then compare your final answer with mine. Go and think. Please take your time and finish the problem. Thank you. Well, that was a really excellent question. I know you put a great deal of effort into it. I hope you have been able to solve it. For the first part, you will certainly be in agreement with me. After that, you might have taken the common denominator approach. I will proceed with a different method for the rest, but my final answer will definitely turn out to be the same. So let us go and see what exactly we need to do. All right, in the denominator, we have a single x term. The term x plus 1 to the power of 3 cannot be factored any further. X is a first degree term. It has a power of 1, so it will be converted into a single fraction. Next, x plus 1 raised to the power of 3. Although it is inherently a first degree term, because its overall power is 3, I will convert it into 3 separate fractions. And all of them have first degree denominators, meaning each possesses a first degree factor. And because they are first degree, their numerators will all be constant values. So it becomes b over x plus 1, c over x plus 1 squared, and d over x plus 1 cubed. You see, it has now transformed into 3 distinct fractions. Do not make a mistake. Since the factor is first degree, the numerator will simply be a number. So I will find a common denominator. What does that actually mean? Their common denominator will be x times x plus 1 to the power of 3. And then we write the numerators over this common denominator. What does that mean? The first denominator is x. So what is it missing? It needs x plus 1 cubed. So we multiply its numerator by x plus 1 cubed. I will not fully expand that here. The left numerator must be equal to the right numerator. The left numerator is x minus 1, and the right numerator is the expression we have. These must be equal to each other. One way is for me to expand the x plus 1 cubed terms. I need to arrange the x's together, the x squared terms together, and the constant numbers together. It is possible, but a bit long. There's another approach we can take here, which is to substitute x with a specific number. If we choose this number wisely, many of our calculations will be significantly simplified. For instance, what kind of number? I will go ahead and substitute 0 for all the x's. If I substitute 0 for x on the left side becomes minus 1. Then if I substitute 0 for x on the right side, something interesting happens. Only a remains. Why is that? Because all the other terms on the right side contain x. And when I set x to 0, every single one of them disappears. Only a is left. So right at the start, the value of a was obtained. The value of a was found to be negative 1. Okay, I will carefully consider what number to use to make my calculations a little easier. And this time we will set x to excellent negative 1. Because if I substitute x with negative 1, then some of the terms, in fact, I can say all of them, will become 0. Except for the very last one. That is, if you set x to negative 1, the left side will become negative 2. On the right side, the terms involving a, b, and c will all become 0 and vanish. What will remain? D. So d is also found. D is 2. All right, I already have a and I also have d. I will choose 2 more numbers and then b and c will be found. This specific number might not make a huge difference, but naturally, it is always better if you choose numbers in such a way that the coefficients become smaller. For instance, if I were to set x to negative 2 and then substitute x with negative 2, the left side of the equation would become negative 3. The right side, negative 2 plus negative 1 to the power of 3 equals negative 1. Negative 2b plus 2c minus 2d. I will substitute a and d, which I have already found, into their respective places. Then I will substitute 1 for all the x values. This gives us an equation where if you set x to 1, the left side becomes 0. Again, the right side of the equation is expressed in terms of a, b, and c. I already have d and a, so I will substitute them into the second system of equations, solve it, and b and c will both turn out to be 1. So my fraction is decomposed. Well, this was fraction decomposition. We want to see what we should do now that we have encountered integrals of rational expressions. So in the first section of lesson 4, we learned the method of partial fraction decomposition. We discussed how exactly we go about decomposing these fractions. We write a separate fraction for each of the factors in the denominator. the numerator's degree is always 1 less than the degree of the denominator factor. If a denominator factor has a power, we write as many fractions as that power. Now let us proceed to examine precisely how we can effectively utilize this method when we are dealing with the integration of rational fractions. The fundamental question arises, what exactly should our course of action be if we encounter a fractional expression? So upon observing a fraction, our very first and crucial step is to carefully assess whether it is capable of being factored or separated into simpler terms. So, is it possible to decompose the fraction or not? That is, can we use the partial fraction decomposition method I taught you or not? If the fraction can be decomposed, the first step is to decompose it. Now that we have decomposed the fraction, what do we do? It says that after you have decomposed your fraction, one of the situations I am about to describe will occur. It says that if the degree of the denominator is 1, we take the entire denominator as u. And of course, this statement that I am making is also true for this case. If the degree of the denominator is 1 higher than the degree of the numerator, so if you see a problem where the denominator's degree is exactly 1 more than the numerator's, then take the entire denominator as u. And so, just like before, what do? Once we have taken the entire denominator as u, we then calculate du. Then we substitute. The answer will then appear in the form of a natural logarithm, ln. Now, I will solve this using the very example we have. All right, second case. If the denominator is a first degree factor with a power, meaning a linear term in parentheses raised to a power, what do? We take the expression inside the parentheses as u. We have done all this before, and I have already taught you all the substitution methods. What else might we see? It says that if the denominator of the fraction is a non-repeated quadratic factor, this second degree term should appear only to the first power. For now, we are dealing with a non-repeated second degree term. It says that if you encounter such a case, that is, if you see that the denominator is ax squared plus bx plus c and the numerator is a first degree expression, it says to separate this as ax over x squared plus bx plus c plus a constant over the same denominator. Now, what does it tell you to do next? It says, well, you have now created two separate integrals, integral number 1 and integral number 2. To solve integral number 1, you should take the entire denominator as u. This is exactly the u-substitution case where the degree of the denominator is 1 higher than the degree of the numerator. What should I do to solve the second one? To solve the second one, we will proceed by the completing the square and arctangent methods. We have already solved all of these in previous sections, and we are just summarizing them. We will do that here, and then we will go through some more examples. It states that if the denominator of the fraction contains a repeated quadratic factor, meaning you have a quadratic expression raised to the power of n. What are we doing here? Again, we write a numerator ax over the entire denominator plus b over the entire denominator. So our first step in any case is that we have separated our expression. It becomes a quadratic term raised to the power of n, and its numerator is always ax plus b. Sir, why is your numerator consistently ax plus b? Well, I already explained this when we discussed partial fraction decomposition. I mentioned that when the denominator is a quadratic expression, once you decompose it, the numerator will certainly be a linear term. So please do not come back and ask me, sir, why are you always placing a linear expression in the numerator? Because I have already performed the decomposition. When I performed the decomposition, when the denominator is an irreducible quadratic factor, I had certainly told you that the numerator must be of degree 1. So I separate the numerator as ax plus b over the parenthesized term in the denominator raised to the power of n. I write ax in one fraction plus b in another fraction. Oh, okay, so how are we going to solve the first one? To solve the first one, we need to consider the expression that is found within the parentheses, u. To solve the first one, we take the expression inside the parentheses as u. To solve the second one, we are going to use a trigonometric substitution, the t method. Which ones were those exactly? We complete the square first, and then after applying the trigonometric substitution t, we use those forms a sine theta, a tangent theta, and a secant theta. Now, I'm going to solve some examples of these so that it really sinks in well. Let us imagine this is the result after performing partial fraction decomposition. For the moment, we are not actually going through the decomposition process. Just suppose that we have already arrived at this simplified expression, 5dx divided by 7x plus 4. It is very straightforward. The denominator is first degree. I am going to take the entire expression in the denominator and set it equal to u. Good. Now, if we take the derivative of 7x plus 4, we get 7dx, and that is equal to du. What do we have in the numerator? We have a 5 on top. It is of no use to me. I will take the 5 out of the integral. I wanted to make a 7. I put the number 7 in front and its reciprocal behind it. I put 7 in the numerator and its reciprocal 1/7 right behind it. It is 5/7. Now, what was the name for the numerator 7dx? Excellent, it is du. The denominator is 7x plus 4, which is u. We have calculated the integral of du over u many times, and it becomes natural log of u. Another example. It is dx in the numerator, and in the denominator we have 5x plus 3, all raised to the power of 4. Which model does this fit? The denominator contains a linear expression, which is raised to a power greater than 1. Go through the different models that I've already explained to you and see which specific model it matches. Look, I already told you exactly what you need to do. We are going to take the quantity 5x plus 3. U is supposed to be the entire expression that is under the power. If you set 5x plus 3 equal to u, then tell me the next step. We take the differential, so 5dx is equal to du. We put a 5 inside and its reciprocal 1/5 outside. So numerator is du and the denominator is u raised to the power of 4, then moves up to the top and becomes u raised to the power of minus 4. Add 1 to the power and divide by that same new power, and then we can move forward. Or finally, we replace u. Let us move on to the next example. All right, consider the integral of x plus 3 over x squared plus 4. Check which model this belongs to among the ones I have taught you. Everyone find its form. Well done. The denominator is a quadratic without an external power. What did I say we do? We separate the numerator x plus 3 into x over x squared plus 4 plus 3 over x squared plus 4. Well done. It has been transformed into several simpler fractions. Two fractions, good. I already told you how we solved the first fraction. The degree of the denominator is 1 more than that of the numerator. Excellent. We take the entire denominator as u, and its derivative needs to be in the numerator. But we do not have 2x dx there, do we? So we put a 2 in and a 1/2 outside. It becomes du over u, which gives natural logarithm of u. And do not forget that 1/2. The first term is 1/2 times the natural logarithm of u. Now let us move on to the second. I asked, what is the second one going to be? Go back and check the solutions that I provided to you. X squared plus 4. Aha. A squared plus x squared. Arctangent. Excellent. That is it. What did the arctangent formula have? It had a 1 over a term. So it is 1 over a times arctangent of x over 2. Excellent. Let us move to the next model. Once again, its denominator is a quadratic expression, and this time it has a power. Go find out which model I taught you. Yes, a second degree polynomial that has a repeated factor. What did we say we do in such cases? We said that in these situations, we separate the 2x term. Then we have minus 3 divided by that factor. Now we are going to solve these one by one. What was our plan for this? We have two separate integrals here. As you can see, to solve this first integral, I will take the expression under the power, which is x squared plus 9, and set it as u. All right, from this point forward, everyone must go really fast. Well done, it becomes 2x dx. So du is exactly 2x dx. Nothing is missing, and there is no need to adjust anything. It is du over u squared. You can really see how much we've improved since your very first days here. That was just the first part, and there is another part. 3 over x squared plus 9 raised to the power of 2. Now, what did I tell you we should do in order to solve it? Yes, that is right. X to the second power plus 9. Which model is this? A squared plus x squared. Excellent. That is absolutely right. Now, what was the trigonometric substitution we used for a squared plus x squared? X is 3 tangent theta. Dx is 3 times 1 plus tangent squared theta times d theta. Those who do not remember this method should rewatch lesson number 3. In lesson number 3, I taught trigonometric substitution. Oh, right. What happened then? There was a 3 in the numerator of the question, and we factored this out because it did not serve any purpose inside the integral. So in the numerator, dx became 3 times 1 plus tangent squared theta times d theta. In the denominator, we have x squared plus 9. Now, since x is equal to 3 tangent theta, then we have 9 tangent squared theta plus 9. From the denominator, I factor out a 9. If I factor out 9, what remains is 1 plus tangent squared theta. Remember, 1 plus tangent squared is equal to 1 over cosine squared. And in the numerator, I also had a 1 plus tangent squared term, which I then simplified with the denominator squared term. So what exactly did we end up with after all that simplification? What remained was 1/9 of the integral of cosine squared theta. As I said in previous sessions, to calculate the integral of cosine squared, we use the power reducing formula. You can see I have written it here. Instead of cosine squared theta, we must write 1 plus cosine 2 theta. I will also pull out the 1/2 since it is a coefficient, and with the 1/9 it becomes 1/18. It became 1/18 theta plus I expanded sine 2 theta. The formula for sine 2 theta was 2 sine theta cosine theta. It has a 1/2, so it becomes sine theta cosine theta. And here is the final result of our integral. But as I mentioned to you in the previous section, since the original problem was given in terms of x, this answer must also be expressed in terms of x. Therefore, we need to convert all of these thetas back into x once again. But how exactly do we do that? Or was it that we had initially assumed? We had taken x to be equal to 3 times tangent theta. So tangent theta then becomes x divided by 3. That is excellent. This question is also providing a good review of our previous lesson. Tangent theta is equal to x over 3. Now what was tangent again? It is the opposite side divided by the adjacent side. So the opposite side here is x. With the help of Pythagoras, I will find the hypotenuse. That is it. Cosine is adjacent over hypotenuse. Excellent. Sine is opposite over hypotenuse. All right, what exactly were we discussing? We had set our x equal to 3 tangent theta. In our solution, we arrived at theta. Well, how do we find theta? I said whenever you want theta itself, you look at what you set x to be. We very easily use its arctangent. What had I set my x to be? 3 times the tangent of theta. Therefore, theta became the arctangent of x divided by 3. And I substituted that back in. Now, please pay close attention. The final result of the integral was 1/18 of theta. So this is theta plus sine theta multiplied by cosine theta. I found cosine theta with the help of my triangle, and I also found sine theta using the same triangle. I can then easily substitute these values, and the result of the integral will be obtained. Let us move on and solve another problem. The integral of 2x plus 5 over x squared plus 4x plus 5, all raised to the power of 2. So what should we do with this? What do we have in the denominator? An irreducible quadratic factor with a power. Look at the methods I have taught you. Look at the patterns. See which model it is. What was the first step? Yes, that is correct. For the very first step, I am going to rewrite the numerator. I will write 2x over the quantity x squared plus 4x plus 5, all squared plus 5 over the quantity x squared plus 4x plus 5, all squared. But we could have used a clever trick here, which is a clever maneuver was actually employed to solve this question. What was that clever maneuver? I am looking at it. I'm going to take what is inside the parentheses as u. So if I take what is inside the parentheses as u, its derivative is 2x plus 4. I can take advantage of the 5 up there. What should I do? I will give 4 of that 5 to the 2x and separate the 1. If I were not sharp enough for this trick, we could still solve it like the previous problem. But if you are careful, our calculations will be much less, simpler, and more manageable. So here I will write my 5 has 4 plus 1. I will move the 4 to the left. Hi, I'm separating the 1. Now we are going to proceed with the solution. In the first integral, I will take the entire denominator as u. So its derivative becomes 2x plus 4. Do we have that in the numerator? Yes, you can clearly see it is right there, so there is no longer any need for me to add and subtract a 4. I have already placed the 4 there myself. So my first integral has been transformed into du over u squared. What about the second integral? For the second integral, I will complete the square in its denominator. Our instructions told us what to do with problems where the denominator is quadratic and the numerator is a constant. Go ahead and use trigonometric substitution. How did we use trigonometric substitution in our previous session? First, we would complete the square. If we complete the square, I can take x plus 2 as tangent theta. If I take x plus 2 as tangent theta, and then differentiate both sides, dx will be equal to 1 plus tangent squared theta times d theta. Now we will proceed with the substitution. The numerator, dx, will be substituted. Yes, that is 1 plus tangent squared theta. The denominator, well done. You will substitute x plus 2 with tangent theta. So what did we end up with? Once we simplify, we are left with 1 over 1 plus tangent squared theta. This is quite familiar to us now, isn't it? After working through so many examples. It becomes 1 divided by cosine squared theta. So the whole expression simplifies to cosine squared theta. So the integral becomes the integral of cosine squared theta d theta, which we rewrite using the double angle formula in terms of cosine 2 theta. I have calculated this using the golden formula 3 times already. Therefore, to prevent us from wasting time, I have only written the final answer. I have also calculated the integral of cosine squared 3 separate times in previous problems. Using the golden formula, the result was 1/2 multiplied by theta plus sine theta cosine theta. I have already calculated sine theta and cosine theta for you in the previous problems. Since this section is exactly like the previous problem, specifically the one right before this, I did not write it out to save time. Okay, so we have been given an integral where the numerator's degree is 1 greater than the denominator's. We said that a fraction where the numerator's degree is greater than the denominator's degree is called an improper fraction. We divide the numerator by the denominator. The numerator of a fraction should not have a higher degree than the denominator. We all know how to divide. We divide the numerator by the denominator. Then we write the result as the quotient plus a fraction, where the numerator of the fraction is the remainder of the division, and the denominator is the same as the original denominator. The denominator has been factored as x times x minus 2 times x plus 2. We are now solving a problem where the denominator is also factorable. In our previous examples, the denominator was not already in factored form. We were practicing each step individually. Now we want to incorporate the factorization process and solve the complete problem. Okay, if x plus 2 is the first term, its integral is clear. X squared over 2 plus 2x. This is the first part. What do you see in the second part? For a fraction with 3 factors in its denominator, what should we do? We need to decompose it. Since it is degree 1, it transforms into 3 fractions, and because each factor is degree 1, its numerator is just a number, a over x, b over x minus 2, and c over x plus 2. Well, I have worked a lot on partial fraction decomposition with you. I expect that here we can easily find a, b, and c. My suggestion is to find a common denominator. Then set the numerators equal to each other, and by plugging in numbers, you should determine a, b, and c. I will wait for a few moments here. Please pause the screen. Each one of you must solve this problem completely on your own. Do not wait for me to give you the answers. I truly want all of you to successfully find the values of a, b, and c. Excellent. Thank you for taking the time to find a, b, and c. Let us quickly review what you have found together. We found a common denominator, we multiplied the numerators, and we set the left side equal to the right side. Now I will substitute 0 for x this time. Why? Because when I set x to 0, both b and c will disappear. Once b and c are eliminated, a can then be found 1/4. Now what number will I substitute for x? I will assign the value 2. You might have chosen different numbers. When you substitute 2 for x, once again, 2 of the parenthetical terms will become 0, and only the variable b will remain. From this calculation, the value of b will be determined as 1/8. I truly hope that all of you have arrived at this exact same result. And once again, we set x to -2. Then 2 more of the parentheses will be eliminated. What is the value we get for c? -3/8. Alright, the fractions are now separated. You can see I have written out all the fractions consecutively. Now they are all set and ready for integration. Which particular model would this be? Excellent. A model where the denominator is a first degree polynomial. When the denominator is of the first degree, if I take the entire expression as u, it can be solved very easily with the help of the natural logarithm. The first one is the natural logarithm of x. The second one is the natural logarithm of x minus 2. And the third one is the natural logarithm of x plus 2. Let's move on to another example. Well, once again, we have been given an expression that has not been factored. The very first step in solving fractional integrals was to decompose the expression, if it was possible to do so. This expression still has not been factored, so we absolutely must factor it now. Oh, what is in the denominator? A factor raised to the power of 2. As we have said, when there is a factor with power n, we must write it n times. Since the numerator is first degree, a and b are sufficient for it. Its decomposition becomes a over x plus 1 plus b over x plus 1 squared. And then c over x minus 2. Now the task is clear. First, the common denominator. Everyone please find the common denominator. Now, the left-hand side will be set equal to the right-hand side. Yes, everyone, please write it down exactly as it is indicated here. Now let us go ahead and assign some values. What kind of numbers would be best for us to use? I believe by now everyone has gained enough experience with this. We will choose values that make the terms inside the parentheses equal to 0, so we can calculate things much more simply. For example, we will assign the value of x to be 2. Perfect. If we assign x the value of 2, c will be equal to 1. Excellent. What other number can we substitute for x? -1. Very good. Now everyone, go ahead and substitute -1 in place of x. From this point, b is determined to be -1. And what other value can we possibly substitute here? We can indeed set the value of x to 0. If we substitute 0, a will also be found to be -1. The fraction has now been decomposed and is completely ready for us to integrate it. Okay, we have three fractions to consider. The first one is negative dx over x plus 1. This is our very first integral. Negative dx divided by the quantity x plus 1 squared. For a and b, I substituted -1. And 1 over x minus 2. This is our third integral. The first integral with its first degree denominator becomes, by the rule, negative natural logarithm of x plus 1. The second one has a second degree denominator. If we take x plus 1 as u, tell me the derivative of x plus 1. Good! Do you have dx in the numerator? Yes, we have an extra negative, which we will keep aside for now. It became negative du over u squared. Then u squared comes up, and we already know its integration method. U to the power of -1 over -1. Do not forget that negative sign in front. Okay, the third one is dx over x minus 2. And its denominator, which is first degree, what was it? That is right, the natural logarithm. So, we have now computed our three integrals, and the operation connecting them is addition. Let us move on to another question. I will guide you through the beginning, then each of you will solve it on your own. We have dx divided by x to the 4th power minus 16. Can the denominator be factored? Yes, it can. How many factors are there in the denominator? There are 3 factors, and one of them is quadratic. There are 2 first-degree terms. For each first-degree term, its numerator will be a constant value, a divided by x minus 2, and b divided by x plus 2. And for the second degree term, its numerator must be of the first degree. So we write cx plus d over x squared plus 4. So the numerator is first degree. Now take a common denominator. You have already seen the common denominator. We would multiply all of these terms together. The numerator of the left-hand fraction is 1, and we will set it equal to the numerator of the right-hand expression. The numbers we can provide are 2, -2, 0, and 1. Don't rush. Carefully place each of the numbers and make sure you perform the addition and subtraction operations absolutely correctly. If you have managed to do this work properly, then A will become 1/32, B is -1/32, D is -1/8, and C is 0. So we have found A, B, C, and D. We will now decompose our fraction. I have substituted the numbers for A, B, C, and D. Now the first term we obtained was 1/32 times dx over x minus 2. The second term we got was -1/32 times dx over x plus 2. And then the third one, -1/8 times dx over x squared plus 4. The first denominator is of degree 1. You all know this very easily. Tell me, what does the first one become? Good. We have the natural logarithm of x minus 2. And the next one is the natural logarithm of x plus 2. And for the final one, we have x squared plus 4. It is like a squared plus x squared. Do you remember what the integral for that formula was? The inverse tangent function. Very well done indeed. It is 1 over a times the inverse tangent. So the result is 1/16 of the inverse tangent of x over 2. Now let us move on to the next example together. We are looking at the integral of x squared minus 4, all divided by a 5th degree polynomial term in the denominator. The very first and most crucial step we need to undertake is to factorize this entire algebraic expression. All right, so if we proceed with factorizing the expression, specifically focusing on the denominator, and we extract an x as a common factor from it, what will then remain is a 4th degree polynomial. If we look closely, the remaining expression is a perfect square. It becomes 2x squared plus 1 all squared, all right? Now that the denominator is factored, we can easily perform the partial fraction decomposition. We have an x here, and then we have a quadratic expression, which is raised to the power of 2. X is separated on its own. Then we have a second degree term with a power of 2. Since we have a second degree term, its numerators must be first degree. Because we have a power of 2 here, we must write this expression twice. So I have already written one instance of it, bx plus c. all divided by the quantity 2x squared plus 1. And for the second one, we write dx plus e all divided by the quantity 2x squared plus 1 all squared. And now that the separation has been completed, we are back to finding the common denominator. As per our agreement, we will find the common denominator for each term, and then we will set both sides equal. If you have taken a common denominator and then set the two sides equal, you can once again solve this problem by equating the coefficients on both sides, especially since it is the final question in this particular section. You are absolutely free to substitute numerical values. It really does not matter. I set the corresponding coefficients equal. What does that mean? Right, so the coefficient of x to the fourth power on the left is 4a plus 2b, and the coefficient of x cubed is 2c. On the right-hand side, there is no x to the fourth term, so I set this coefficient equal to 0. I did the exact same thing for the x cubed term. I did exactly the same procedure for the x squared term. I did the exact same for x and for the constant term. Now, if you compare these expressions term by term, your a, b, and c values will be obtained. A is -4, and B is 8. Everyone, please review your answers. If your answer happens to be different from mine, go back and double check it. Do not just overlook it. Go back and check again to understand why your answer was different. A is -4, B is 8, C is 0, E is 0, and D is 9. Okay, let us take its integral, and then we will close this part. I will put the numbers I found in place of A, B, C, D, and E. 3 fractions were created. In the first fraction, the denominator is first degree. We had said that if the denominator is first degree, then this becomes the natural logarithm. So it is -4 times the natural logarithm of x. Let us move on to the second one. Recall from the lesson summary and the problem types I showed you. If the denominator is degree 2 and the numerator is degree 1, what is our approach? Exactly. We take the entire denominator as u. We find its differential in the numerator. It becomes 4x dx. If du is 4x dx and the numerator is 8x dx, then it is 2 du. U is in the denominator, so it becomes 2 times the natural logarithm of u again. What is u? Excellent. 2x squared plus 1. And the third one is a degree 2 expression squared. I said, what do we do in these situations? We take the expression under the power as u. Then I will find its derivative and substitute that result into the numerator. This will then transform into du over u squared. Now, if we rewrite u squared as u to the power of -2, its integral can be computed quite easily. I truly hope you have thoroughly understood all the lessons from this section. Make sure you achieve a good level of proficiency, and then we can proceed to our next lesson. I will be seeing all of you very, very soon for the next part of our course. You have not forgotten what we have been discussing, have you? Exactly. Math is all you need.